All right, moving into Lewis structures. And we've already talked about a little bit with the Lewis dots and how Lewis dots work. So we know that we're only working with things that have S and P electrons. We're not going to be talking about things that have D and F electrons because of what I've talked about already. But that was the Lewis dot structure basics. Okay, and just to remind you, if I have oxygen, oxygen has 6 valence electrons. Remember, oxygen normally has 8 electrons. We don't count those 2 electrons that are on the lower shell. So for oxygen, okay, oxygen itself has 8 electrons. Okay, but now when I talk about Lewis structures, I've got to represent molecules using this type of representation. So what I'm going to do is I'm going to pull out something fun, okay, something that we're all familiar with, something that we call water. All right, now water's Lewis structure is H2O. And remember from previous video talks, the 2 here represents that we've got 2 hydrogens. Okay, and there's no number here, which means that I've only got 1 oxygen there. So H2O, 2 hydrogen atoms, 1 oxygen atom, bound together. So how are these things going to work in a Lewis structure? So I've got the oxygen listed there. Let me go ahead and throw the hydrogens on. We know that each hydrogen has a dot because it's only got 1 valence electron. Okay? So remember John Lewis structures, the first thing you want to do is you want to identify all the atoms that you've got and how many electrons are used in bonding. And the electrons that are used in bonding, for the most part, this is a generalization. It's not a hard and fast rule because there are exceptions, but the electrons that we use at first are going to be the ones that are not paired. So each one of these hydrogens, obviously we've got to bond those electrons to something, and these electrons on this oxygen, those ones we're going to have to bond to the oxygen somehow. Okay? The second rule, the second thing we have to take into account is something that we call the octet rule. And I grabbed a dead pen. There we go. I'll just throw that on the floor because I can't hit a trash can. Octet rule. All right. The octet rule states that any atom in the second row, that's an important caveat, anything that's in the second row is going to have a maximum of 8 electrons. It can have under 8 electrons. That's okay. There are times when that happens. But the maximum possible electrons is 8. Okay? So second row elements must have a maximum of 8 electrons. Okay? So that's a must. Now, when I get to third row, this moves from being the octet rule to the octet guideline. Okay? The guideline being is that usually you're going to see 8 electrons with anything third row and above. So third row elements usually have 8 valence electrons. And remember, when we talk about 8 valence electrons, we're talking about just S and P. Because when you get into third row, fourth row, fifth row, you might even start incorporating D electrons. And if you incorporate those D electrons, guess what? You're over 8 electrons at that point. So don't count those. Don't count the F electrons either. Just S and P electrons. Okay? So third row elements usually have 8 electrons and above. So this goes for fourth row, fifth row, sixth row, 18th row if we ever get to there. Those elements as well. Okay? All right. So how do we connect everything here? So we look at this oxygen. And the oxygen itself has 6 electrons there, represented by electron dots. The hydrogens have 1 dot each. So what am I going to do? Easy. I'm going to move this electron up there and this electron over there. Okay, and in doing so, what I now have is water represented like this. There's my oxygen, and it's got 1 electron here, 1 electron there, and I'm going to have hydrogens. Okay? All right. Those electrons are being shared by the hydrogens and the oxygens. And the sharing is actually quite important. This represents a covalent bond. Okay, so let's call this thing what it is. These electrons are shared, and at this point we run into the covalent bond. Right? And we know this is covalent because covalent bonds, all they have are electron bonds between two nonmetals. Okay, so the two nonmetals are hydrogen and oxygen. Okay, easy enough? Good. So now I'm going to ask Dr. Ruane, what about metals and nonmetals? And I'm glad you asked. I especially like the fact that you start waving your hands in front of the computer. Yes, I can see what you're doing. So let's see. Let's take oxygen again. All right. Here's oxygen. Here's its two electrons. Here's another electron. And what I'm going to use this time is sodium. All right. And sodium I'm going to represent as blue. And sodium has one electron in each. All right. Now, because of the electronegativity difference between oxygen and sodium, the oxygen is actually going to be stealing the electrons. Nonmetals steal electrons from metals. Okay? So it's going to steal the electron away from the sodium. And that's okay because the sodium now goes to that stable configuration of its core elements. Okay? It drops down, sodium loses that, and suddenly it's got 10 electrons. It's actually very happy. It looks like neon at this point. So the electron actually runs over here to the oxygen, and what I'm left with is something that's an ionic bond. And an ionic bond means that there are formal charges on this oxygen. The oxygen has stolen two electrons away from the sodiums. So the electrons no longer belong to those sodiums, they belong to the oxygen. Notice that nothing here is blue. As a result, because that oxygen has two extra electrons, it's got that full orbit that it wants, but you have to account for those two extra electrons, so oxygen is represented as a -2 charge. Okay? The sodiums are going to be stuck somewhere around the oxygen, and they are stuck there to charge balance this compound. So sodium has a plus charge, both of these things have plus charges, and they're going to be stuck to counterbalance the -2 charge that's around the oxygen. Okay. Now if I were to write this as a molecular formula, I would represent this as Na2O. Okay. Sodium oxide at that point. Okay. So those are basic Lewis structures. The rules are actually very simple here. And for these rules, we look at this and we say, okay, doesn't seem so hard. Well, let's try a more complex example. See what you think about that one. All right, my complex example at this point, I have C2H6O, also known as, or it could be known as ethanol. So that's one of the structures, right? It could be also known as dimethyl ether. So let's look at a couple of ways we could draw this, because there's more than one right answer here. Welcome to chemistry, the land of more than one right answer, okay? There's more than one right answer to the drawing of this Lewis structure. Okay, so let's follow our rules. Good news is that we have everything second row and under, the under being the hydrogen, nothing over third row. So we know we have to follow the octet rule. So the octet rule is firmly in place at this point. All right? Now, draw your Lewis dot structures for each one of these atoms. Okay, go ahead and pause this and try to follow along. Okay, because I'm going to give you some tips on how to draw these things. So for carbon has 4 electrons, okay? Now I've got 2 carbons, so I'll draw the carbons out here. Right? Oxygen itself, I've only got 1. Oxygen generally represented in any molecular diagrams by the red color, okay? Red, if you ever see a red sphere on a map drawing of an element or a molecule, red is oxygen, okay? The ball and the stick type things. And for hydrogen here, hydrogen, I'm going to draw as purple here so you can see it. A lot of times it's represented as white, sometimes it's pink. I'm going to draw this as purple in this case. And I've got 6 hydrogens. All right. Now, the first thing I want to point out is what happens if I stick two hydrogens together. Okay? So I'll stick two hydrogens together, I'll stick these two guys together, make a covalent bond, and what I now have is this. Alright. Is there any way for these hydrogens to bond to a carbon or an oxygen? No. What we've made in here is hydrogen gas, H2. And hydrogen gas will not be able to do anything else. So, the first rule that we've learned is never bond hydrogen to itself. Because if you do, you get hydrogen gas and it floats away and doesn't become part of your Lewis structure that you're trying to draw. Okay, so don't do that. Don't put two hydrogens together. Okay? Alright, so that means that these hydrogens that are out here, and this goes for halogens too, chlorine, fluorine, bromine, iodine, all of those in hydrogen are considered terminuses. They're terminals. They generally don't do more than one bond to something. Okay? So I'm going to highlight this and I'm going to say one bond. Okay? Now what about that red guy, that oxygen, right? How many electrons does it need to get that full happy octet that we were representing earlier? Well, it's got 6, right? An octet sounds like 8, so it must be 45, right? No, not 45. Somebody didn't eat dinner. You need 8, right? So it's got to absorb 2 electrons there in order to get to 8, either by ionic bonding or covalent bonding. We have no metals here, so it's got to be covalent bonding in this case. Okay, so it's got to take 2 electrons. So this one needs 2 electrons, or it's going to form 2 bonds. Okay? Now what about the carbons that are up there? All right, how many electrons do those carbons need in order to get to that full octet that we need? That's right. Each one of them is going to need 4 bonds. For the carbons up here, we're going to need 4 bonds. Right. So for each one of something that makes a multiple number of bonds, that's going to be something that we're going to call a non-terminus. These are things that are in the central part of the molecule. So when you're drawing Lewis structures, make sure that your Lewis structures actually start out with the carbons in the center or the oxygen in the center. You need something with more than one bond. You can't start with the hydrogen in the center. So pick carbon, pick silicon, pick sulfur, pick nitrogen, pick phosphorus. All of those are going to have more than one bond that you could possibly start with. Okay? Don't start with any halogen, don't start with hydrogens, because all those start with one bond. Okay? It's easier for you to start drawing with something that's got more bonds. And I always start when doing this thing with something that's going to form the most bonds possible in that grouping of atoms that I've got. In this case, it's carbon. Okay? So I'll start with a carbon here in the center. Right? I know some of you are looking at that and saying, great, we've got a carbon, put all the hydrogens around it. No, don't. Save hydrogens and halogens for last. The reason being is that they can only form one bond. It's better to just make up space with extra electrons in order to get that to work. Okay? So I've got carbons there. Okay? Let's put another carbon next to it. And the reason I say this is because I'm an organic chemist and I know carbon likes bonding to other carbons. Make infinite bonds with other carbons. Things like polymers. Okay? Hello, water bottle made of polymer. All this is just nothing but carbon chains. Okay? So, I'm going to put another carbon next to it. Okay? And what I'm going to do is I'm going to draw a bond stick between 2 electrons to represent that both of those electrons are tied up in a covalent bond. So there we go. Covalent bond between those 2 carbons. Okay? Now let's put the oxygen somewhere. And I'm going to take the oxygen, stick it at the end here. I'm going to make a train of these. There we go. All right? And I'm going to make a bond between that carbon and that oxygen. Okay? So now at this point, if I do that, I've used all of my multiple bond atoms. And then what do I have to stick in that's left? Are 6 hydrogens. Where am I going to put those? Guess what? 1, 2, 3, 4, 5, 6. So let's put the hydrogens in. Okay? And voila, I have the molecule ethanol. Now guess what? There is another molecule that you can draw from this that's not ethanol. Okay, but if you reorganize these in a different structure, you'll get dimethyl ether as well. Why don't you go ahead and try that? Okay, and then I'll get into some more complexities with the next video.